Good afternoon, everyone. Particularly the people on Zoom. So at least for the series of my students presenting, last one, best one. It's a pleasure to introduce you to Mr. Christopher Nieters. So we call him Chris all the time. So the Christopher part becomes more difficult. Chris joined my lab at the very beginning. And he's from Laramie, Wyoming, where he completed his bachelor's in botany at the University of Wyoming. He had been involved in CEA for a long time. During his undergraduate project, he actually worked with several crops, particularly in growth chambers. And since then, he had been working in the industry, highlighting all his potential in terms of scientist and professional. Not sure if you all know his background, but he does have a very nice looking professional website, www.chrisnieters.com.
Right now, it's in an updating phase. It needs to be updated. It's pretty bad right now. You can go if you want.
So it's pretty easy because you have your he has his resume over there, so everybody can take a look at his professional qualifications, and had been contributing greatly with one topic that we will talk today, that is nutrient management and hydroponics. Chris has a lot of great professional qualities, but for our surprise, he's a true soccer fan. He's probably the one in my lab that likes soccer the most, even more than the Brazilians. He does like the English Premier League, is a Manchester City fan. We know that he plays guitar. Yeah, right. We know that he plays guitar whenever I listen to him playing, though. He bakes and also enjoys fly fishing. So without further ado, I would like to give the floor to Chris to enlighten us in his research project. Chris? It's yours. Click it there.
All right, thank you, Ronito, for your introduction. Appreciate it. Lighting squared away here. Thank you, guys. Thanks everyone for showing up today. I appreciate it. As Ronito mentioned, today I'm going to be covering my project, which is focused on managing hydroponic nutrient solutions in controlled environment agriculture. So to get started today, I'm going to give a little background and justification on why we're interested in controlled environment agriculture and some of the reasons we chose to investigate these particular topics that we chose. After that, I'll go into my specific research objectives, which I have 3 of them that I hope to accomplish throughout the course of my research. After that, I'll go into a little bit more detail on each of the chapters. The first chapter is going to be focused heavily in a vertical farm production system. The second chapter is going to be focused in a greenhouse production system. And then I'll leave a little bit of time at the end if anyone has any questions or comments. Okay, so to get started, we may be asking, why are we interested in controlled environment agriculture and growing our crops in places that are protected from the elements? I'd say the most pressing reason is for reasons of food security going forward. It's estimated that by the year 2050, the human population is going to exceed 9 billion people. In that same amount of time, it's predicted in a report from 2018 from the FAO, which is the Food and Agriculture Organization of the United Nations, that in that same time, we're going to need to increase our food output by nearly 60%. So currently, where we're producing a lot of our crops, I'll give an example of spinach and lettuce, because those are the crops that I'll be focusing on for my work. We're growing them in areas that are facing increasingly more erratic temperature regimes. So for example, for spinach and lettuce, we're growing them in California and Arizona, both of which are undergoing mega droughts currently. So with controlled environment agriculture, it allows us to grow some of these crops in areas where we wouldn't traditionally be able to produce them. We can produce them a lot closer to where the majority of these populations are located. So we can reduce a lot of our food mileage by growing them closer to people, as well as reduce some of the food waste associated with transporting these foods to the consumers. As we can see here, this is an example of a vertical farm production system. This is a good example of how these systems can allow us to use a lot less land. This is a company based out of California, actually, and they're growing all of their plants on these 30-foot tall towers that they have on conveyor systems that go by these LED lights. As I said, this allows us to grow a lot of plants in a very small footprint. And the area I'll be focusing most importantly on for my research is that a lot of these controlled environment ag systems use hydroponic techniques, meaning that they're dissolving their fertilizers in a water solution and then recirculating them through the plants to provide the nutrition, as opposed to traditional systems that use the soils to provide the nutrition. So that's what I'll be focusing on heavily with my research. So it may seem pretty straightforward. Using hydroponic techniques, it should be as simple as you find your target nutrient solution, you dissolve it in your water and supply it directly to the plant roots. But unfortunately, over time, what can happen is you can run into some nutrient imbalances that happen because all of these nutrients are not taken up at the same rate. And this actually here is an example that is from a paper published on tomatoes produced in hydroponic solution. On our x-axis, you can see here we have our time and days after transplant. On our y-axis, we have our nutrient uptake from the nutrient solution. And we can see that each of these lines here represents a different macro element. And you can see that over time, we see large differences in these uptake rates. So what that means for us is over time, these nutrient solutions become imbalanced, which can lead to deficiencies, which can ultimately impact our crop growth and development, which is not something growers need to be dealing with. So one common method that growers are using currently to overcome this issue of the nutrient imbalance is to simply dump out the entirety of their nutrient solution and fill it up with a fresh solution where the composition of each of the nutrients is correct. But unfortunately, this simply dumping out of all your nutrients is not a sustainable option going forward. So one major issue with dumping out your fertilizer solution is obviously nutrient pollution. As we can see on a map here, a study that was done here in 2014 showed that our national waterways, 40% of them were rated as poor for sustaining aquatic life due to elevated levels of phosphorus, because as we're dumping our nutrient solutions, we're introducing elevated levels of phosphorus and nitrogen, which can do things like introduce harmful algal blooms. These algal blooms can do things like produce harmful cyanotoxins, which can be detrimental to the health of the communities they're exposed to. They can also lead to zones of hypoxia. So essentially what happens is this nutrient-rich water causes these algal blooms, and as they're decomposing, all these microbes that are decomposing the algae take all the oxygen out of the water, which makes it very difficult to sustain any ecological life in those areas. So simply dumping out our nutrient solutions isn't a sustainable way to be managing our nutrient solution. And beyond damage to ecosystems, it's also not a good economic model to be dumping fertilizers down the drain. As some of us may have seen over the last year, the prices of fertilizer have gone up almost 60% for a lot of them. So it's a very expensive commodity that farmers can't afford to anymore, just be pouring it out. They need resources so they can understand how to manage this resource efficiently. It's not only expensive, but it's also, not something we can continue to extract indefinitely. A lot of these nutrients, there's these minerals that we're extracting from the earth for fertilizers. We can't keep extracting them at a indefinite rate. So an example can be shown here with rock phosphate extraction. Rock phosphate is the most commonly used phosphate source for industrial agriculture. And based on a study from 2009, they showed that based on the current global reserves of rock phosphate, we're going to reach a peak. According to a USGS survey, we could reach a peak of our phosphorus production by the year 2025. So we'll still be, coming up. So we'll still be able to continue to extract rock phosphate, but it's going to become more and more difficult to access these areas, increasing costs. So when you combine these things, if we need to increase our food production, we can't be contaminating our ecosystems, and it's going to be more challenging to access some of these nutrients. We need solutions that allow us to effectively manage our nutrient solutions to produce our food. So currently in controlled environment ag, there's kind of a broad range of approaches that people are using. in the industry to manage their solution. And they kind of range on a spectrum from like very targeted controls to more of a broad control. So for example, for targeted controls, you have systems where you're sensing your pH of your solution, your EC, which is like your electrical conductivity, which people use as a proxy for the amount of fertilizer in solution. And then you just have on the other hand, you have more like of a broad control where people aren't necessarily controlling and dosing individual nutrients, but they're actually just, maintaining enough of their nutrient solution in their reservoirs so the plants have access to water and nutrients. So again, on this side, we're not necessarily looking at individual elements that are taken up. We're just supplying enough of water and a base level of nutrition so the plants are able to produce their life cycle. And then on the other hand, we can have a more targeted approach. So basically what my research is going to be doing is emulating kind of a range of these different methods and see how these different nutrient solution management strategies impact our water use, our fertilizer use, as well as how they impact plant performance and plant yield. So now I'll go into my specific research objectives that I have for my project. So research objective 1, I want to identify nutrient solution strategies that will allow us to use less water and less nutrition, but at the same time not sacrificing our yield and plant performance. My second objective is to compare nutrient management strategies in different production systems. So I want to compare nutrient management strategies in a vertical farm production system and a greenhouse to see. Growers have a lot of different information that they can draw from this research, so it'll be more broadly applicable. And then finally, I want to investigate the impact of crop lighting levels on nutrient dynamics, because depending on the operation, people have different grow conditions and production systems. So I'm hoping that by doing investigating these different production methods, lighting, and strategies, we can understand, people will have a lot of different insights they can take away from the research. All right, now I'll move on to chapter 1, which will be in a vertical farm. To start with, we didn't have a vertical farm. We only recently finished up building our vertical farm. As you can see here, we kind of just started with an empty room, and this room actually used to be divided into 2 even smaller rooms. So a lot of work had to be done, removing walls, reinstalling walls, sealing all the walls and the floors. And actually, if we get to the photo on the far right here, we actually were able to, install all the equipment and get our vertical farm up and running. And I just want to take this opportunity for everybody involved. Almost everybody in Dr. Ferrarezi's lab had some hand in helping get this constructed. And not only Dr. Ferrarezi's lab, at various points we've had help from Dr. Van Ursels' lab, as well as Dr. Lombardini's lab. So a big shout out to everyone who is involved, because this would not be possible without everyone who helped put it together. So a little bit more of the setup. We actually got a very generous donation from Agrify to donate. I think they donated over 280 individual luminaires for our trial. So they helped us furnish not only the second vertical farm where I'll be conducting my research, but they're also provided the lights for our first vertical farm. But again, I won't be sharing any preliminary data today because a lot of this setup that we started in September has taken us till now to get together. But essentially what we have now is, this is the outside of the vertical farm, and essentially all of these gray rectangles you see here are the LED drivers and different control systems that will allow us to control our vertical farm to very tight set points, which is very typical of that would replicate kind of an industrial type of system. So here's kind of an image of what the vertical farm setup looks like. We have 4 separate racks here, and then you can we've separated them into different compartments. And you can see here, based on the background shading, we're able to hit different light levels in each of these compartments. So that's how we'll be achieving supplying different light levels, and see how that impacts our nutrient management strategies. So for each of these, also these black rectangles represent a deep water culture system. So we'll essentially be putting the plants on a styrofoam raft, and then they'll just be floating with their roots suspended in the nutrient solution. Each of the reservoirs will have a air stone that will be supplying oxygen, so the roots have access to good dissolved oxygen levels. We also have really good airflow. One challenge that comes with growing this many plants in a very small area is that the airflow can be less than ideal, getting it through all these tight areas. So in order to supply adequate amounts of air, so we have adequate transpiration rates, we've installed, if you look on the top level, we have convection tube fans. And essentially what this is a bilge blower fan that's attached to a long tube of plastic. And then actually some work that was done by some of our French students that were here over the last summer, Camille and Esteban. They helped us develop and calculate the diameter of the holes and how many holes we would need to achieve very uniform airflow over all of our plants. So that's what we have on every layer. So we have uniform airflow over all the plant canopy. So having this kind of testing bed will allow us to, each of these deep water culture trays will have a separate management strategy. So we'll be randomizing all the different nutrient management strategies across the different light levels. Okay, now we'll get into a little bit more detail on the treatments themselves. So I'll be testing 6 different nutrient management strategies that I'll go into a little bit more detail on the following slide. I'll be testing 3 different light intensities for the vertical farm. It'll be relatively low at 250, 500 ppfd, and 750 ppfd rather. As I mentioned earlier in the talk, I'll be testing 2 leafy green crops. It'll be a butterhead lettuce variety, as well as a spinach that has been shown to produce fairly well in these type of environments. So I'll be able to have 4 replicates of each of the individual light intensity by nutrient solution management strategies, and it'll be in a complete randomized block design. Okay, so the nutrient management strategies. As I talked about when I got started, there's a lot of different levels of control where we have kind of broad porch control, where we're essentially just refilling our reservoir and making sure the plants have access to nutrition, to more targeted control, where we can get as fine as, we send these, our reservoir solution in for a lab analysis, and then whatever is missing from our targeted levels, we can add individually back to the solution. So essentially what we're going to do is be comparing all these different management strategies against a control. My control for this study is going to be, they're all going to have the same starter solution. The only thing that's going to vary across these different management strategies is the method we use to refill them. So we're starting all with the modified Sonneveld solution. And in the case of our control, we're going to actually be doing a drain weekly. So this is kind of emulating, like I mentioned, what people are doing now. We're dumping that solution out and refilling it back with our starter solution to ensure that that treatment is just consistent throughout the duration of the plant growth. And then as we go down, we'll be getting more and more details into our management strategy. So for treatments 1 and 2, we'll simply be filling them up weekly to a predetermined level of about 6 gallons. The only difference between treatments 2 and 3 is that treatment 2, we're going to be refilling with a full strength solution. Treatment number 3 will be a half strength solution. The rationale there is if you're refilling with a half strength solution, some of those nutrients that are not taken up as quickly, you'll avoid oversupplying some of those if you are not refilling with a full strength solution. It's a common method that a lot of growers use. It's kind of hands off, but has also helped you not use as much fertilizer waste. So treatment 4 rather, we're starting to get into a little bit more control. So we'll be refilling it up weekly, and then we'll be dosing it back up with our nutrient stock solution to hit a target EC level. And this is a very common method that's used in the industry, where you'll just have a submersible EC probe, and then you'll have a system that's automatically tracking when your EC target gets below a certain level, it'll dose your nutrients back up to a particular solution. So that's what we'll have for treatment number 4. Treatment number 5 will be similar to that. We'll be dosing it back to an EC target, but we're going to be using a mass balance approach, which I'll give a little bit more detail on that on the next slide. But essentially we'll be dosing it back up to an EC target that's been guided by the plant growth rate and the plant transpiration rate essentially. And then finally, the most targeted control we're going to do is we're going to be regularly sampling these treatments. As I said, sending them in for lab analysis. And then when we see which specific fertilizers have been taken out of solution, how much water they've used, we will refill them back to the initial target level of this modified Sonneveld. Okay, this is just a quick introduction into the mass balance approach for treatment number 5. Essentially what it allows us to do is for each of these crops, you have specific amounts of each of the major essential elements you want in your plant tissue. And then based on how much your plant has grown and how much has transpired, it gives you an idea of how much of your nutrients, or how much of each of the nutrients you want in your solution. So a more broad way of saying that is if you have a plant that's not necessarily putting on a lot of biomass, but it's just mostly transpiring water, you're not going to need to add those nutrients back because they're still going to be in solution. So that's kind of what informs the mass balance approach. And it's just another way where you can essentially use plant growth and plant transpiration to inform how to actually manage your nutrient solution. So a little bit more targeted. Okay, so and then here the data metrics I'll have for this chapter are kind of broken into three separate categories. Plant growth and performance is going to be pretty standard horticultural data metrics I'll be taking. Leaf area, shoot and root dry biomass, and fresh biomass. I'll also be including some leaf gas exchange to look at how these different light levels are interacting with the gas exchange rates. I'll also be taking some chlorophyll A fluorescence to see how these different light levels are affecting plant performance and how that's impacting yield and the dynamics of all of our different management strategies. I'll also be doing leaf tissue analysis. So I'll be taking handheld meters and getting anthocyanin, chlorophyll content, as well as we'll be sending in leaf tissue analysis to see how these different management strategies are actually affecting the nutrient composition of our dried leaf tissue. And then finally, obviously, we're going to be doing a lot of analysis on our nutrient solution. So we'll be tracking the water use, the nutrient use for each of our treatments. We'll also be tracking the nutrient concentration. So as I mentioned, we'll be sending them in for regular analysis. Then I'll be tracking solution EH, PC, and pH, EC, and the dissolved oxygen content. Okay, growth conditions. I won't belabor and go through each of these details, but it is important to note in many vertical farm setups, it's very common to grow at elevated CO2 levels. Since it is so expensive to control the environment in vertical farms, if you enhance your CO2 concentration in your room, it allows you to grow the plants much faster and get more plants out the door. So it's a much more economical way for plants to be grown. So that's one major difference we'll see between the first chapter and the second chapter that'll be carried out in the greenhouse. All right, and I'll move on to chapter 2. So essentially what we'll have for chapter 2 is it's going to be a mirrored design of chapter 1. So all the nutrient solution management strategies, all of the light levels are going to be the same. The only real difference is going to be the variability of the environment of the greenhouse. And along with that, we won't be able to enhance with CO2 because with ventilation, any CO2 you enhance with will likely be just vented out. So with our greenhouse setup, we won't be able to do that. But like I said, everything will be identical. Same crops will be grown and the same amount of plants in a completely randomized block design. I'll show a little bit more on this slide. So we actually had lights donated to us from another lighting company as well. Rain Growing Systems enabled us to have these different, this is an overview, a light model of the light levels we'll be able to achieve with our supplemental lighting. So as I said, we'll be able to randomize each of these deep water culture trays across these different systems in order for us to conduct the trial in the greenhouse. We may have some issues, depending on the time of year, we'll also be dealing with the supplemental light, or sorry, just the sunlight coming into the greenhouse. So what we'll likely have to end up doing is looking at DLI calculators and using some shading so we can hit those lighting targets for each of our treatments. But we still need to get all these lights installed, so there'll be a little bit more to come on this once we get to that part of the setup. And again, the growth conditions will be a little bit more variable. That's the big thing to take away here, as I mentioned, because as we're looking at these plots here on the right are showing some of the environmental data taken from Greenhouse 13 over the last couple of months. And we can see that there's a fair amount of variability we'll see. So that'll be part of the project. We'll be comparing, is a particular nutrient management strategy, is it the same? Is it just as effective in a vertical farm where you have very controlled conditions, or do you need different strategies, when you're growing in a greenhouse where things are a lot more variable? So that will be one thing that we'll be investigating as well. And then again, I want to say a big thank you to Rain Growing Systems and Agrify for donating the lights that made all this research possible. And then with that, I'll open it up to any questions or comments.
Maybe you can start with the online audience, checking if they have any questions for you.
I don't see any in the chat here.
Does anyone online has a question for Chris and would like to start?
I got a question. What do you think is going to be the best management strategy?
I think the more targeted ones are going to be more effective. But in our case, it's a lot easier to do these by hand, but if you're in a commercial production system, you can't hire someone to do this. You'll have to automate it. So there'll always be a trade-off between like what's most effective for maintaining your nutrients versus like that upfront capital of integrating that system. So I think it'll probably be a trade-off, what's most effective from the grower perspective, but from nutrient use and water use, the more targeted approaches I think are going to be more effective.
Do you have any idea what the initial solution, what is inside, like nitrogen, phosphorus stuff?
I don't know those levels off the top of my head, but it's a pretty standard solution. I think it's around 150 ppm nitrogen. The other components I'm not as familiar with, but I would have them off the top of my head.
Close to 190 potassium, close to 90 calcium, standard average nutrient composition.
So how about the micronutrients? Do you have any?
Yeah, they're all provided as well.
You mentioned about the MS, the nutrients. Usually traditionally they have a whole gland solution, which you use. Is there any difference? Whole gland solution?
Can let him answer it, then I can compliment.
Yeah, sure. I don't know the differences between those two. I know that one's not used as commonly in the more recent literature. I think some changes have been made that make for I don't want to say a better solution, but less people are using that now. But Ronita may be able to fill you in on why people are transitioning away from the Hoagland solution.
Yeah, we do have to select a fertilizer solution. So there are many different options going. So we looked over what is the current fertilizer solution recommendations for leafy greens due to the characteristics of the crops it's growing. So Hoagland is very standard. So the levels might fluctuate a little bit. Both solutions, either Hoagland or the modified Sunnyvale that we are using, they're both okay for plant growth. Hoagland had a smaller micronutrient concentration. So some of those varieties for hydroponics, they actually have hydrocarbons. But honestly, despite of the potential differences in small micronutrient concentrations, you would be totally fine using Hoagland as well.
Thank you.
Do you ever have organisms other than plants take advantage of your nutrients?
Oftentimes, yes. The algae really enjoy our systems. It's part-times as an algae growth system. We try to minimize the amount of algae growth by keeping the solution as covered as possible. So that foam raft we have fit as close as we can get cut to the corners. And then each of we're using rock wool plugs and little net pots that cover up most of the exposure to the solution, but we do get a fair amount of algae growth in these systems. It's kind of hard to avoid. You have to start to get into like using like a peroxide and filtration systems to really get them out. So it's pretty challenging. So yeah, they'll probably be taking away some of the nutrients as well. So it's something we'll have to consider if one particular treatment gets a lot more than the others. Oh, I think you were next, sorry.
So the samples which you are planning to send for the nutrient analysis, let's say for leaf tissue, is it like for one particular time point or like over a time period?
Yeah, so I think for the leaf tissue analysis, we'll be doing at less time points, but for specific treatments, like for, are you asking just specifically about leaf tissue?
Yes.
Yeah, so for leaf tissue, we won't do those as frequently. We'll probably have like 2 time points about 2 weeks into the growth cycle after they've been transplanted, and then another one at the end of the trial. Since we have so many treatments, so just the cost of sending in that many samples is going to be prohibitive. So we'll likely only do 2 time points.
So what do you envision in terms of impact of this research for production facilities? So going on a granular level with your control, it's certainly going to save a lot of fertilizers. Do you have an idea in terms of number of savings or potential savings?
No, I don't have anything like that, but what I'm hoping is that, not every, commercial operation is going to have the capital that they'll be able to get these advanced targeting systems. So what I'm hoping to provide the general growers is depending on their system, like what the trade-off is for each of these systems, because if you may not have a vertical farm, you may have a greenhouse where you can't monitor these things. So what I want people to understand is what the impact is of these different management strategies. So but that'll be something, since we'll be tracking the water and the nutrients, it'll be easy to calculate the savings from each of them. So yeah, hopefully it's broadly applicable and people can take a lot away from all these different treatments. So.
For the treatment where you're just dumping solution and then refilling, do you plan to take any measurements before you dump of what is the EC?
Yeah.
And how it's decreasing over time, or I don't.
Yeah, so actually for the entirety of the trial, especially when we're kind of figuring out how quickly, because we're also going to be controlling the pH of these different solutions. So I'll be monitoring the EC and pH of all of them, probably every other day almost, just to get an idea of how things are changing. But yeah, I'll be tracking that as well. All right, unless anyone online has any more questions or comments.
Thanks, everyone, particularly people online, for joining us today. Enjoy the rest of your afternoon.
That's good.